Okay, hi everybody. If you've got questions over the in-class review, we have two options. We can either talk about them now, which I'll be glad to do. Also, though, I have posted the solutions to the in-class review on Blackboard. Two students did excellent work on that, so I posted their solutions. So anybody can jump in. We can look at that, or I also have the final exam review sheet nearby, and I'll be glad to answer questions off of that. Yes, sure.
Hello, sir. I have a question on the final review
Okay.
on the question number 10. What's it delta y?
Delta y is just how much the y coordinate has changed. So if x is equal to, if x is equal to 2 and delta x is equal to, was it 0.2? Oh, 0.02. Then that means that I'm going over an interval from 2 to 2.02. So delta y is just going to be f of 2.02 minus f of 2. That's how much the y coordinate has changed. On the other hand, dy is the differential, f prime of x dx, and that'll be f prime of 2 multiplied by 0.02. So the delta x and the dx represent the same quantity, but delta y and dy do not. So delta y is exactly how much y has changed, and dy is an approximation for how much y has changed. And I've noticed that in physics classes, the professors often will replace delta y with dy as just a quick estimation for how much something's changed.
Okay, I got it. Thank you.
Sure thing. I see a lot of the people who are attending turned in the review. Good for y'all. Who else has a question?
Where did
Chris?
you post the solutions?
They're in the week 15 study plan. Are they visible now? They should have become visible at 11:45.
I don't see them.
Let me look. Maybe I might have done 11:45 p.m. instead of a.m. I can see if I did it right. They're showing visible in mine. They're right below where it says bonus point relay answers. Below that it says bonus point relay solutions. And just above where it says bookwork 12.
It says error on them.
You cannot see it, or it says error when you click on it?
It says bonus point, final exam bonus point relay twice. One of them says error, and the other one doesn't say anything.
That is bizarre. I'm not looking at your screen right now. This is in the honors class you're looking, right?
Yes, sir.
So I see final exam review, oh sorry, higher below that. Bonus point relay answers, bonus point relay solutions. I think I can look at this from the student viewpoint, see what it looks like from your side. It's looking normal from my side. Is there anybody else in the room who can go and look in the week 15 study plan and see whether you can access the bonus point relay solutions?
I'm looking at it right now, sir. It's up for me, but
And you two are in the same class.
Yes, sir.
I don't know, Chris S., you might want to try exiting Blackboard and going back in. I don't know.
Okay.
You're getting an error also, Krishna? Let me look in your class. Um, what browser is everybody using? I wonder if
Using Chrome.
you're using Chrome, Chris S.
Yes, sir.
I'm using, actually, yeah, I'm using Chrome for this window also. Bees
Oh, now
are.
it's on there. I see it now.
Krishna, you might want to check again. Chris said that he can get to it now. I have it set to open at 11:45. Maybe it's just taking a little bit longer for some reason. Yeah, I'm looking at it from the student view in both classes, and it looks normal in both classes.
Yeah, I can see it now.
Okay, good. It must just be taking a moment to roll out. So like I say, I'll be glad to answer any questions y'all have on that or on the review sheet or out of the book. Some of you might not have finished the most recent homework. At least one person in the room is going back as far as related rates problems, practicing that a little bit more. Because y'all should expect either a related rates problem or a maximum problem on the test. One of those two kinds of word problem.
On the final review, 2D.
Oh yeah, so this is similar to a problem y'all had on the most recent test.
It looks familiar. I haven't tried to work it yet. It just looks complicated.
So let me just give you, the main trick is to expand it all out using rules of logs before you take the derivative.
Okay.
Now, is that going to be a hint, or should we look at it? Should we do a step or two of it?
You can do a step or two of it.
Okay. Let's see if I can get it down. So I has natural log of x squared sine x times the square root of 2x plus 3 all over x squared plus 4 ln x. So tell me if this is going too fast for expanding it. I could write this as log of x squared plus natural log sine x plus natural log of 2x plus 3 to the half minus natural log x squared plus 4 minus natural log of x. And then using the power rule, I can bring this 2 down, and I can bring down that 1/2. And when we take derivatives, we're going to use the fact that the derivative of natural log of u is u prime over u. So in the first case, this will be 2 times 1 over x plus, we take the derivative of sine of x, the sine goes to the bottom, and its derivative, cosine x, goes on top. On the next one, the derivative of log of 2x plus 3, 2x plus 3 goes to the bottom, and its derivative 2 goes on top, minus x squared plus 4 on the bottom, its derivative 2x on top, and then finally, natural log of x on the bottom, and its derivative 1 over x on top. And then we can simplify it a little bit, just writing that as 2 over x plus cotangent x, and so forth. Does that make sense?
Yes, sir.
Cool. A couple of people did this correctly on the test, just using the chain rule, but it was way, way, way harder to do it that way. I can't remember how you did it.
That's the same question on the test?
I don't know. There was one similar to that on the test. The one on the test might have been slightly easier, but similar. But some people did it the hard way, and they still got it right. There's definitely one similar to that on the test. For those of you who turned in your homework, I graded some of them this morning. Some of you had it in either overnight or fairly early this morning, so you might want to look in Blackboard. I didn't mark mistakes very much, but if you did not get a half point for a problem, that means that you made at least one mistake in there. So you could either ask me questions about that now, or you can compare it to the solutions that are posted. But in the relay, I did not go through and mark a lot of mistakes. But if you're not getting full credit is a 0.5. So if you're not getting 0.5, that means that there's a mistake in there. Karina, I have not gotten to yours yet. You're one of the folks that turned it in around 9:30, and I didn't get to those. So Karina, do you want the review, not the relay, correct? The one about the 13-4 ladder should be 13-foot ladder.
Yeah, the related rate problem.
Good. You're definitely not the only one in the room who wants to practice related rates. So this one might look familiar to you because it's similar to the common assignment that we did earlier in the semester. I'm just reading it, make sure I've got it. So the ladder is 13 feet long, and when the base is 12 feet from the wall, the base is moving at 5 feet per second. So let's just draw it like this. It's 13 feet long, and when I label my picture, the things that are constant, I'll go ahead and label with their length, but the things that are changing, I'm going to label with variables. So since the distance of the base from the wall is changing, I'm going to give it a variable named x, and the distance from the floor to the top of the ladder is changing, so I'm going to call that y. But since the ladder is 13 feet long, I'm going to go ahead and give that a constant label. So it says when the base is 12 feet from the wall, the base is moving at 5 feet per second. So when x is equal to 5, dx dt is, sorry, did I have those backwards? Yeah. When x is equal to 12, dx dt is 5. Then it wants us to find how the top of the ladder is moving. Okay, so let's write down an equation that just relates to x and the y. That would be the Pythagorean Theorem. X squared plus y squared equals 13 squared. And then to relate the rates, I need to take the derivative of each side of this equation with respect to t. And on the right side, the derivative of a constant is 0, so I get a 0 on the right. On the left side, I'll have 2x dx dt plus 2y dy dt. And now let's just plug in everything we know. We know that x is 12 feet, so that's 2 times 12 we know that dx dt is equal to 5 plus 2 times y times dy dt equal to 0. And it's the dy dt that we're looking for. But we don't yet have what to plug in for that y. But with the Pythagorean theorem, from this equation, we know that if x is equal to 5, we have 5 squared plus y squared equals 13 squared. So what, at that moment, y squared is going to be equal to 144, so y is 12. And that gives us the number to plug in here. So 2 times 12 times 5 is 120, plus 24 dy dt equals 0. So 2y dy dt is negative 120. Oops, that's not 2.
Is it
That's
is
20.
it 5 squared or 12 squared when you're finding for y?
Oh man, you are so right. You're so right. I'm glad you're watching me. So x is 12. So this is a 12. This is 144. This one's the 25, and it's y equals 5. I got those exactly backwards. So that's a 5 right here. And that's 10. So assuming I've corrected things, it looks like dy dt is going to be negative 12 feet per second. And that negative corresponds to the fact that y is getting smaller as the top of the ladder is moving down the wall. So other than the mistakes, does that make sense?
Makes sense. Thank you.
Okay. What else do you have? Let's look at that one, Krishna. So, oops. I was looking at 15. You said 13, right? Oh, no, you did say 15. So you want to do that function summary sheet, basically?
Yeah.
Okay. So x to the fourth minus 4x cubed plus 10. Let me just scan over the problem, make sure that I see everything we have to get. So we want increasing, decreasing, local minima, local maxima. So that's all first derivative stuff. And then we want concave up, concave down, and inflection points. And that's all second derivative stuff. I think we can do that. So let's do all the first derivative stuff first. F prime of x is going to be 4x cubed minus 12x squared, which is the same as 4x squared times x minus 3. Now you're going to need to watch me as closely as Karina did, make sure I don't make a mistake. A polynomial is never undefined, so I don't need to worry about where the derivative is undefined. But I do need to find the places where this derivative is 0. And that's going to happen when x equals 0 and when x equals 3. So at both of those places, the derivative is 0. And now let's test intervals. So I need to pick a point in each of these 3 intervals and then plug it into the derivative. So maybe over here I can pick -1. And here I can pick 1. And over here maybe x equals 4. So if I take f prime of -1, I get 4 times 1 times negative 4. That's negative 16, but I guess all I really care about is the fact that it's negative. If I plug in 1, I get 4 times 1 times negative 2, and that's a negative number. And if I plug in 4, I get 4 times 16 times 1, which is positive. Does everything look right so far?
Yeah, yes.
Okay, so if I'm looking at increasing, decreasing, I see that the derivative is negative on these first two intervals. So f is going to be decreasing on negative infinity to 0, and also on 0 to 3. And a great question I get is whether you can put those together. And in this case, we can. It's decreasing from negative infinity all the way over to 3. If I wanted to picture what was happening, the function is decreasing, and then it flattens out, and it decreases some more until I get to 3. And then at 3, I have a minimum, and the function starts increasing again. So it is decreasing all the way from negative infinity to 3. And f is going to be increasing on the interval from 3 to infinity. Now when I classify the critical numbers, 0 is neither a max nor a min, because it's decreasing and then decreasing some more. However, over at 3, I have a local minimum using the first derivative test, because the function changes from decreasing to increasing. So that means I have a relative min when x equals 3. And the minimum value will be f of 3, whatever that is. So 81 minus 4 times 27 plus 10. You can put it in the calculator. And that's all we get from the first derivative. Now the second part of the problem, or the last several questions, we're all asking for second derivative information. So let's look at f double prime of x. I'm going to differentiate this version of f prime. That'll give me 12x squared minus 24x, which is 12x times x minus 2. And then once again, I'm going to set that equal to 0. Well, there are two places where that's equal to 0. It's equal to 0 at 0, and it's also equal to 0 at positive 2. So now my number line is for f double prime, and I've got zeros at both places. And then we test intervals again. So maybe over here on the left, I'll pick negative 1. In the middle, 1. And on the right, 3. So f double prime of negative 1 is going to be negative 12 times negative 3, which is a positive number. If I take f double prime of 1, that's going to be 12 times negative 1, which is a negative number. And when I plug in 3, I get 36 times 1, which is positive again. So in terms of concavity, the function is going to be concave up when the second derivative is positive, which is from negative infinity to 0, and also from 2 to infinity, and it's concave down in between from 0 to 2. So kind of looking at my picture on the left, it's concave up until I get to 0. Then it's concave down. And then here at 2, it becomes concave up again. So that's reasonable based on my picture. Concave up, concave down between 0 and 2, concave up past 2. Now, since at each of these places where the second derivative is 0, the function changes concavity, that means that both of those points represent points of inflection. So one point of inflection is going to be at 0, comma f of 0, and the other one is going to be at 2, comma f of 2. The first one's easy. F of 0 is 10, so that's the point 0, 10. And then 2, you just plug into the function. That'll be 16 minus 4 times 8 plus 10, whatever number that is. Looks good? So that was number 13 on the review sheet. A couple more people have come in. I'll be glad to answer questions on the review sheet or the relay or out of the book. Just jump in. By the way, the solutions to the relay are on Blackboard now, if you look in the week 15 study plan. 6H. Ah, good, some integrals. Oops, I was looking at I. E to the 3x minus e to the x over e to the 2x. And I'm going from 0 to log 3. You know, Chris, this one seems to use a strategy we might have talked about before. Check. The first thing I'm going to do is split this into two parts as e to the 3x over e to the 2x minus e to the x over e to the 2x, just breaking up the fraction. Then I'll simplify each fraction. Subtracting exponents, 3x minus 2x is just x. And on the second fraction, e to the x minus e to the 2x is e to the negative x. Now, the part I kind of remember talking with you about, Chris, I'm not positive, is that here, for the second exponential, I need to do a u sub, u equals negative x. But this first exponential doesn't need a u sub. So what I'm going to do is break this into the sum of two different integrals, or actually the difference. So I'll have the integral from 0 to log of 3 of e to the x dx minus the integral from 0 to log of 3 e to the negative x dx. This is slight overkill, but I'm going to call this first integral I1 the second integral, I2, and then I'll combine them later on. I'll just do the integrals one at a time now. So integral 1 is the integral from 0 to log x of e to the x dx. And antiderivative of e to the x is just e to the x. This will go from 0 to log of x, log of 3. So I have e to the natural log of 3 minus e to the 0, which is 3 minus 1 or 2. So the first integral is 2. And then for integral 2, I'm going from 0 to natural log of x of e to the negative x dx. And this is the one that requires a U-substitution. I'll let u equal negative x, so du is negative dx. So I need to multiply by a negative 1 right here. And I can cancel that by multiplying by another negative 1. And then notice that if x is equal to 0, and I plug that in here, I get that u is also 0. And if x is equal to natural log of 3, then u is negative natural log of 3. So let's plug all that stuff into this integral. I'll have negative the integral of e to the u du taken from 0 to negative natural log of 3. So the integral of e to the u is just e to the u. So I have negative e to the u taken from 0 to negative natural log of 3, which will be minus e to the minus natural log of 3 plus e to the 0. That's feeling right. Using rules of exponents, negative natural log of 3 is the same as natural log of 3 to the negative 1 power. So this is negative e to the natural log of a third plus 1. So that's negative a third plus 1, which is 2/3. So all that work, I'm getting 2/3. And then finally, if I take integral 1 minus integral 2, I get 2 minus 2/3. I'm getting 4/3 is my answer.
I have a quick question. For the first integral, do you take don't you have to take the derivative of the natural log x because it's not just straight x, you have to use the chain rule for that, or does this not apply to this one?
I think you're thinking of the fundamental theorem of calculus part 2. So I kept making the mistake in writing an L up there, but the upper bound is a natural log of 3, not a natural log of x.
Oh, okay, thank you.
So, oops. If I were to squeeze in a problem that's working the way that you're thinking, if I had said find the derivative with respect to x of the integral from 0 to natural log of x of, I'm just going to say u squared du, then it's indeed true that you would take that natural log of x and plug in for the u, so it'd be natural log of x squared, and then you would multiply by the derivative of that exponent. But notice that that's a different kind of problem, Karina, one where you're trying to take the derivative of an integral where the variable is showing up in the bounds of the integral.
Okay, thank you.
This
Yeah, that
one's,
makes more sense.
yeah, this one is Fundamental Theorem of Calculus Part 1.
How did we get to the ln of 1/3?
That's actually sneaky in here. Let me see if I can pull out that one part. Do you believe this negative natural log of 3 that I got?
Yeah, I don't know how you did that either.
Okay, so let's back up.
Okay.
Notice that the upper bound for x was natural log of 3,
Yes.
and my substitution was u equals negative x. So if x is natural log of 3, then u is negative natural log of 3. So that's where this negative natural log of 3 came from.
Okay.
And then the power rule for exponents says that k times natural log of x is the same as natural log of x to the k. So negative 1 times natural log of 3 is the same as natural log of 3 to the negative 1 power. So I'm bringing the coefficient in and writing it as an exponent. So that's natural log of 1/3. So negative natural log of 3 is the same as natural log of 1/3.
Okay.
If you wanted a similar problem, just squeeze one more down here before I completely erase this. What would be another way of writing negative 2 natural log of 5?
The ln 5 to the negative 2.
Good, which is the same as what?
2/5.
I'm sorry, I didn't hear that.
2/5.
Nope. 5 to the negative 2 power is 1/5 squared. So that'd be natural log of 1/25. So negative 2 natural log of 5 is the same as natural log of 1/25.
Okay, I get it.
Okay. I'm going to clear out this. I'm going to clear this mess. It's too full. What else do you guys have? We still got a half an hour. There's plenty of time. We can do some more.
Can we do number 16 from the review?
So I've heard 16 and 6b. Yeah, let's look at 16 first, and then don't let me forget 6b. So 4x cubed plus 2x plus 3. Okay, so in the book, this is corresponding, I think, yes, to section 4.1. This is called an initial value problem. So you begin by finding an antiderivative of F prime. So the function we're looking for is going to be one of the antiderivatives of F prime of x. So it'll be an antiderivative of 4x cubed plus 2x plus 3. So it's going to look like x to the 4th plus x squared plus 3x plus some number c. And the way we can find out what c is by using this equation, which is known as the initial condition. So we know that f of 1 is equal to 2. So let's find out what f of 1 is. from this previous equation, f of 1 is going to be 1 to the 4th plus 1 squared plus 3 times 1 plus c. And we're told that has to equal 2. So 5 plus c is 2. So it looks like c is -3, if I've done my arithmetic correctly. And then I plug that back in right here. So f of x will be x to the 4th plus x squared plus 3x minus 3.
Wait, where did you get the 2 from?
I'm sorry, where did I get what?
The equals 2 from?
Oh, we were told that f of 1 equals 2. So I plugged 1 into this formula, and I set the result equal to 2. Does that make sense, or that's not making sense?
But it says f of 1 equals -2.
Oh, crap, that's what you're saying. No, that was totally my mistake. It is a -2. So if that's a -2, then this must be a -7. And this will be a -7 over here. Does that look better?
Yes.
Better
Thank you.
and hopefully correct. Okay, let me see if I can find that other one. That was 6D or 6B. B. Okay. So in these last couple sections where you're learning how to do integrals involving exponentials and logs, the exponentials are not really that hard because the integral of e to the x is e to the x. But sometimes it's a little bit tricky to see when to use a U-substitution in a log type integral. And that's going to be what's happening in this problem. We have the integral from 0 to pi over 6 of cosine x over 2 sine x plus 1. And it turns out the best thing to do is a U-substitution. You equal that whole denominator. If you do that, then du is 2 sine x dx. And that just looks promising to me because I have a cosine x dx right here. So I'll multiply by a 2 and divide by a 2. And then that whole numerator becomes du. Everything that I'm circling here, the 2 cosine x dx is du. And that whole denominator becomes u. Now I still have a 1/2 in front. Let's figure out what the new bounds are going to be. If x is 0, then u is 2 sine 0 plus 1, and sine of 0 is 0, so that gives me a 1. And if x is pi over 6, then u is twice sine pi over 1, which is 2 times a half plus 1, which is 2. Oh, so all the hard part's over. The antiderivative of du of 1 over u is natural log of absolute value of u. And I'm going from u equals 1 to u equals 2. So this is half natural log of 2 minus half natural log of 1. Now, natural log of 1 is 0. So we can write this as 1/2 natural log of 2. If we wanted to fancy up the answer, we could write it as natural log of square root of 2. Same thing. I don't know which way the answer is written. Does that help, Akshnur? What else would y'all like to look at? Or if there are just any topics that you'd like us to talk about some, maybe some stuff that the videos weren't clear on that you'd like some more examples of. Has everybody finished up the homework that's due tonight?
I had a question. So
Mm-hmm.
where did the ln absolute value of u come from?
That's the formula that you're just going to have to memorize. And that's that the antiderivative of du over u is natural log absolute value u plus c. And that comes from the very last section that we cover this semester. So if you aren't in the very end of your homework, then you might not have seen that quite yet. Two other ways that you might see that formula is you might see it as the integral of u to the -1 du, or you might see it as the integral of 1 over u du. But all three of those are the same thing. Natural log absolute value u plus c.
Okay.
Yeah. I'm not remembering this section. Section 5.2.
Could you do another integration problem?
Happily. One off the review or one out of the book?
Could you do the one off the in-class review? I think it was 1B.
Yeah, that's one that involves long division. Turns out that's going to be a really important skill for y'all in Cal 2. So it's for us to go over it now. So we have the integral of 4x squared plus 4x plus 5 over 2x plus 1. Man, somebody I graded this morning made a mistake in the long division, but I can't remember. I don't think it was anybody who's in the room right now. So anytime you're doing an integral of a rational function, so you've got a polynomial over another polynomial, if the degree of the numerator is bigger than or equal to the degree of the denominator, then you want to start with a long division. So we've done long division in order to find slight asymptotes. This is just another example of where it's used. To begin with, you take the leading term inside and divide it by the leading term outside. So you're taking 4x squared divided by 2x, which is 2x. You write that on top. Multiplying the 2x times the 2x plus 1, you get 4x squared 2x, and then you subtract. So let me distribute that minus sign. I'll end up with a minus here and a minus there. The 4x squareds cancel, and 4x minus 2x is 2x. Up around the plus 5. Then I do it again. I take the leading term inside divided by the leading term outside. 2x over 2x is 1. So I pick up a plus 1 here. Multiply 1. That gives me 2x plus 1. And then once again subtract. So here I'm distributing that minus sign. And 5 minus 1 is 4. And that's going to be my remainder term. 4 over 2x plus 1. Now this goes back to that trick I was mentioning earlier. Sometimes you have an integral and some parts of it require substitution and other parts don't. So you might want to split the integral up. So many of you might do this step in your head, but I'm just going to make it explicit. The 2x plus 1 is a polynomial, and we can integrate that just using the power rule. The 4 over 2x plus 1, that's going to require U-substitution. So I'm going to break that off into a separate integral. Now the first integral, 2x plus 1, I get x squared plus x, and I'm done with that. And I'll also bring the 4 out of the second integral, so I can focus on the part that requires a substitution. So this is, once again, coming from that last section, 5.2. I need to do a U substitution, letting U equal to 2x plus 1. So I'm letting U equal the quantity that's in the denominator. Notice that du is 2 dx, and I've got a 1 dx. So let's multiply by a 2, and then cancel it out by multiplying by a half. So I'm multiplying and dividing by 2. So now the integral, the 2 dx becomes du. The 2x plus 1 is u. And notice I'm back to this pattern of du over u. So that's going to be a natural log. So I have x squared plus x plus twice natural log the absolute value of u plus c. And I'll substitute the 2x plus 1 back in. And that's what I get. Nobody in the room is asking it right now. Oh, does somebody have a question?
Can we do number 13 from the review? Yeah, 13.
Sure. Rectangle with 3 subrectangles, 300 feet of wire. So first of all, let's see if we can get the picture. Here's the rectangle. I want it divided into 3 subrectangles. So I already drew that line wrong. Let's try it again. There we go. So we've got 300 feet of wire to do this. And we want to maximize the area. So since the idea of maximizing is connected with area, we know that that's our objective function. And the fact that we only have 300 feet of wire, that's what's limiting us. So that's our constraint. So let's introduce some variables and see if we can write this down. Let's let x be quantity. So the distance from here to here. So I've got 4 sets that have length x. And let's let y be the entire length this way. So I've got y on the bottom and also y on the top. So for our objective function, area is x times y. And the constraint will be 4x's plus 2y's equals 300. So a lot of times that's the hardest step. So let me pause to see if that's okay before we move on. Okay with the objective function and the constraint?
Yeah, I'm okay.
Cool.
Yeah, that's definitely the hardest part.
So remember the next step is to solve for a variable in the constraint and substitute it into the objective function. And I think I want to solve for y because I can do that without getting fractions. So 2y is 300 minus 4x. So y will be 150 minus 2x. And then I substitute that in here to get that the area is x times 150 minus 2x, which is 150x minus 2x squared. And now, if I want to, I can even write that as a of x, because the area function is now a function just of x. So to find the points, I'll take a prime of x and set it equal to 0. So the derivative of that is 150 minus 4x. And when I set that equal to 0, I have 4x equals 150. So x is 75 over 2. So 37.5. And if I were to substitute that in right here, I have y as 150 minus twice 37.5, which is 150 minus 75. So y has to equal 75 feet. And I don't look back. It doesn't ask what the maximum area is, but if I wanted that, I would just use the fact that the area was x times y. So I'd have to take the x and the y values and multiply them together.
Okay, thank you.
Auctioneer is asking about 9 and 11. Number 11 might just be questions about definitions. So let me just explain what's being asked for in number 11. And then let's look at number 9 in more detail. So I guess this is kind of a mini physics lesson. But if S of t is position at time t, then the average velocity over the interval, let's say t is going from A to B, would be how far you've moved. So that would be S of B minus S of A divided by how much time has passed, which is B minus A. So if S is position, then you can find out where you are at the 2 points. And then by subtracting them, that tells you how far you've moved. That's what the numerator is. So that's distance. And if you just take B minus A, then that's how much time has elapsed. So distance divided by time is rate. So that's the average velocity. The instantaneous velocity at time t equals c. To get instantaneous velocity, you take the derivative, and to figure out what the velocity is at time c, you plug in for t. So what this should remind you of is the mean value theorem. Yes, Tren, I am recording it. I've just got to remember before I exit to click save on that. So yeah, I'll be posting it. It takes a little while for it to process, but I'll put it up as soon as I get done, as soon as it's finished processing. So I think that should help with number 11, Akshnur. Number 9, I think would be worth spending a little more time on. So x minus 3x to the 2/3 plus 4. I'm going to clear this. And the interval is from -8, oops, to 125/8. And one thing I want you to notice in that problem, number 9, is it says find absolute, maximum, and minimum values. So you ought to already be thinking toward the end of the problem that you're going to be making a table. And that table is going to include those two endpoints, -8 and 125/8. And it's also going to include any critical numbers that you find along the way. And then once we fill out the table, we'll just pick off our biggest value and our smallest value. So that's going to happen anytime it's asking for absolute extrema on some interval. So let's find our critical numbers. F prime of x is going to be 1 minus 3 times 2/3 x to the -1/3, which is 1 minus 2 x to the -1/3, which is 1 minus 2 over the cube root of x. Critical numbers are any place where the derivative is either 0 or undefined. Now notice that this is undefined at x equals 0, and 0 is both in the domain of f, and it's also between -8 and 125/8. So that's definitely one of our critical numbers. We're going to have to add that to the list. And the place where f prime is 0 is going to be when 1 is equal to 2 over the cube root of x. If I cross multiply, that's cube root of x equals 2, which is x equals 8. Now, is that in the interval or not? What's 125/8? Okay, this guy is about 15.6. So that means that both 0 and 8 are in between. Now you notice in some problems you might get a critical number that's either less than -8 or bigger than 125 over 8, or in other words, it's not in the given interval. These are. Now you're going to take each of these 4 numbers and substitute it into the original function to get 4 answers over here. And from that, we'll just pick off the absolute maximum and the absolute minimum. So you had one similar to this on the relay. It was problem number 5. I remember at least one person, I haven't graded all of them yet, but one that I did grade only looked at the critical numbers and forgot to check the endpoints. So just make sure that you're checking both endpoints and critical numbers when you're looking for absolute extrema. So the questions I'm getting are the right kinds of questions. I've gotten both max-min problems and related rates. That's good stuff. I'm getting questions about integrals. I've not gotten much on derivatives. Hopefully that's because you're feeling pretty good about differentiation. I'm also getting function summary sheet kind of stuff about increasing, decreasing, concave up, concave down. The impression I'm getting is that you guys are studying the right stuff. We still have just a few minutes left. Is there something else y'all would like to see before we break?
Can we do 8B?
(8b), is that correct?
Yes, sir.
Sure. So 4 minus x squared over x squared minus x minus 6. And we're trying to find removable and non-removable discontinuities, also vertical and horizontal asymptotes. I guess the easiest thing to do is the horizontal asymptotes. We see that this equation, or this function, is balanced, and that the quotient, or the ratio of the leading coefficients, is -1. So there's a horizontal asymptote at -1. Now, I potentially also have some holes or vertical asymptotes. To find out about those, I need to factor numerator and denominator. I'll factor the bottom as x minus 3 times x plus 2. In the numerator, I might start by factoring out a -1. So -1 times x squared minus 4. So I can write this as negative x minus 2 times x plus 2. Now from this, I can see that there's going to be a hole at -2. So this is a removable discontinuity. If I wanted to remove that discontinuity, I would need for h of 2, sorry, h of -2 to be the same as the limit as x approaches -2 of h of x. That's what it means for it to be continuous, is that the value of the function is to the limit of the function. So that would be the limit as x goes to -2 of negative x minus 2 times x plus 2 over x minus 3 times x plus 2. Factor and cancel. and then direct substitute. So I have negative of -4 over -5, which is -4/5. So that means that there's a hole at the point -2, -4/5. So that's my complete analysis of the removable discontinuity. On the other hand, x equals 3 is going to be a vertical asymptote. And that's pretty much all it asked us to do, and maybe a little bit more. So I have a vertical asymptote, which, by the way, is a non-removable discontinuity. So non-removable discontinuity at x equals 3, a removable discontinuity at x equals -2. So one thing that I'd like to do, you see that little raise hand button on the bottom. I've not used that as a poll before, but if on Friday I were to have a review session from 10 to 11, how many of y'all here would attend? I'm trying to decide whether I need to do that for you guys. So you can just click on that. That'll count as your vote. Yes, you would show up. Okay. I'll take that into consideration. That's about 4 folks out of a bunch of Cal 1 students. I will let you know. What I might end up doing is doing something a little bit shorter than that. But maybe by Friday, more people might have questions than have them today. Because right now you've probably been focusing on the relay sheet and not the review yet. So I think that I can commit to having at least some office time on Friday. It might not be an entire hour for you guys. It might be half an hour for you guys and a half hour for my Cal 3 students. Adjustable. So if you have questions, I am checking the discussion boards every day around 10 o'clock. So if you feel like you don't have a chance to ask a question in conference hours, that's one other way to get questions to me. So feel free to use those discussion boards. Like I say, I check them about once a day, maybe twice a day, and I try to get back to you if you ask a question there. Thanks for showing up today. A lot of you have already turned in the relay, and I'm going to be grading those this afternoon. And Jason, I will be glad to stick around with you for a couple minutes afterwards. Let me go ahead and end this recording.